Here's an interesting circuit for us to analyze. It combines resistors and an inductor, and you might see this as two resistors sort of connected in series, and then there's an inductor in parallel with resistor number 2. In other words, it's kind of like a voltage divider with an inductor in parallel with the second resistor of that voltage divider. Anyhow, the way we've drawn it, there's a switch, and that switch is initially open, so the left part of this whole circuit represents a dead branch, meaning there's no complete path for current to get from point X to point Y in the circuit. Now imagine what's going to happen once we close the switch. As soon as we close the switch, now there is a complete path, and current, we'll say, is flowing in this direction, internal to the battery, continues flowing to the right through resistor number 1, and then reaches a junction. Maybe we'll call this point A and point B in the circuit. Well, when the current reaches the junction, it has two paths that it can take. It can take the path that leads to the inductor or the path that leads to the second resistor. And you might think that the current is going to take the path to the inductor because the inductor isn't a resistor, it's just bare wire that's been coiled up, so it has a negligible amount of resistance. So that's a fair guess. Maybe at first the current all flows through the inductor. In fact, maybe that's the only place the current flows, and the inductor is short-circuiting resistor number 2. Well, it doesn't quite work that way. It turns out that an inductor does resist the flow of current, but it depends. The number of ohms that expresses how much the inductor resists the flow of current is dependent on the rate of change of current. So we know this much. When currents flow in a circuit that have any amount of inductance, then current can't suddenly go from 0 up to some maximum value. Inductance is kind of like an electrical inertia. So in the same way a car can't take off from a red light that turns to green and suddenly go from 0 to 60 miles per hour in no time, the current can't go from 0 to any value in no amount of time. The inductance causes the current to have to rise toward this asymptote. Hey, when is the slope of this graph at its maximum value? Let's see. At which point does this curve have the greatest slope? Oh, all the way back here at the beginning, the slope is greatest. So, interesting, huh? When the current is equal to 0 is when the rate of change of current is equal to its maximum value. And when the current reaches its maximum value, then we extend this graph, we get to a point where the slope is practically 0, so di dt approaches 0 as the current approaches its maximum value. Well, the number of ohms of resistance, and maybe in a future lesson we'll stop calling it the resistance of the inductor and start calling it the reactance, but for now I'll just use the term resistance. The inductor resists the flow of current in a way that's in direct proportion with the rate of change of current. So it's kind of the opposite of the way capacitors behave when connected with resistors. When you have a RC circuit, the capacitor offers no resistance initially, and as time goes by and the capacitor becomes fully charged, it offers infinite resistance. The inductor is just the opposite. Initially, when the rate of change of current is at its greatest value, the inductor resists it infinitely. And eventually, as time goes by, the inductor learns to be comfortable, so to speak, with the amount of current that flows through itself and no longer offers any resistance. So the resistance of an inductor approaches infinity initially when the rate of change of current is at a maximum value. In the steady state, the resistance of the inductor just goes to 0. So that'll help us answer the question now of, in what direction does the current flow? Well, it depends on whether we're talking about the initial condition or the steady state. Initially, as current begins to flow in a clockwise direction and reaches the junction at point A, the rate of change of current is really large, and so the inductor offers infinite resistance, and the current all goes through resistor number 2, and so really you just have a series loop of resistors in the initial condition. However, as time goes by, the rate of change of current gets less and less and less, so the current that flows to the junction splits up, some of it through resistor number 2 and some of it through the inductor. In fact, once we reach the steady state, then there's no longer any current at all flowing through resistor number 2, and the inductor really has effectively become a short circuit. Okay? So if we leave the switch closed for a long time, then the current is just going to flow around the outer loop. Now here's where the problem gets interesting. What happens if we suddenly throw the switch back in to the open position? Well, in that case, the inductor has grown accustomed to having a current flow through it. And to open the switch and suddenly get rid of that source of potential difference that's driving the current, the inductor isn't so pleased with that sort of behavior. The inductor wants to maintain this current through itself. And now the only path that it can do that on, right, this all becomes dead branch with that switch open, so the only complete path for the current to continue to flow through the inductor is through the inductor and resistor number 2. So by suddenly opening the switch, current now appears in R2 again. And the interesting thing is that current, as we'll see in the example problem that follows, can be much larger than the initial current that was flowing through resistor number 1. So let's attach some numerical values and present a few questions so we can try to put this into practice. Okay, so here's the same sort of circuit. The battery is a 12-volt idealized voltage, or EMF. Resistor number 1 is 400 ohms, resistor 2 is 2,000 ohms, and the inductor is half a Henry. Question number 1. What's the initial amount of current through R1 and R2? And call these points A and B. Question 2, what's the initial value of VAB? Okay. Initially. Move on to question number 3. Now we'll say the switch has been closed for a long time. So starting from t equals 0, when the switch is first closed, we get some initial behavior of the circuit, and then we say, fast forward, the switch has been closed for a long time. What's the amount of current in R number 2? What's the amount of current in the inductor? And how much energy is in the inductor? Now we introduce a new time t prime at which the switch is suddenly opened back up. What's the voltage between points A and B? What's the amount of current through resistor number 2? And right at that instant, when the switch is opened, what's the rate of change of current through the inductor? A lot of questions, huh? Let's take it all step by step. I don't think I've given myself enough room to show the work to provide all these answers. So give me a second to space this out. Okay, so this gives you time maybe to copy the questions onto your own piece of paper. Much better. Okay. Well, with the exception of our disappearing parentheses, huh? That's more like it. Okay, now let's tackle the problem. What's the initial current through R1 and R2? Well, initially, there's no current. Oh goodness, what just happened? Initially, there's no current through the inductor. All of the current flows through R1 and R2 as if they're connected in series with each other. So let's see. Ohm's law. Current is equal to voltage divided by resistance. Well, if it's just one series path for the current, then the resistance is just the sum of the two resistors. Okay, so this is divided by the sum of R1 plus R2. Oh, so this becomes 12 volts divided by 2,400 ohms. Well, that's the same thing as 12 volts divided by 2.4 kilo ohms. Dividing by kilo, right? That means division by 10 to the third. That's the same as multiplying by 10 to the negative third. In other words, 12 divided by 2.4, we know that's 5. And then 5 divided by 1,000, we can call it 5 milliamps. Easy. Okay, what's the initial potential difference across points A and B? Well, again, Ohm's law. V equals IR. So from points A to B, we have a current of 5 milliamps flowing through 2,000 ohms of resistance. So 5 times 10 to the negative third amps multiplied by 2,000 ohms. We can cancel 1,000 with milli, and so we're just talking 5 times 2. We get 10 volts. I suppose that means that there's a loss of 2 volts across R1 followed by a loss of 10 volts across R2. After all, this is just a voltage divider. Great. Now the switch is closed for a really long time. What's the current in resistor number 2? That requires no math. This is strictly conceptual. The current is 0. In this case, the inductor acts as a short circuit. Initially, the resistance of this inductor is, for all practical purposes, infinite. But if the switch has been closed for a really long time, then we've reached a steady state. The current that was all going this way past junction A eventually breaks up into two parts, some of it through resistor 2, some of it through the inductor. And as time goes by, the inductor starts to become accustomed to having a current flow through it. At that point, there's no longer any value of di dt, and so the inductor offers no resistance. There's no potential difference across the inductor, and if there's no potential difference across the inductor, then there's no potential difference across points A and B, meaning current no longer flows to resistor number 2. It really has effectively been short-circuited by the inductor. So what's the amount of current in the inductor? Well, then in this case, the path for the current to flow is through resistor number 1, and then through the inductor that offers no resistance. Resistor number 2 has been short-circuited, so we just have current flowing through a resistance of 400 ohms. So Ohm's law says the current should be an EMF of 12 volts divided by a resistance of only 400 ohms. So 12 divided by 4 would give us 3. So 12 divided by 400 gives us 0.03. We can call it 0.030 and recognize this as 30 milliamps. Okay. What's the energy of the inductor at the point in time that the switch has been closed for a really long time? Remember the equation for the kinetic energy of any object? Of course you do. It's 1/2 mv squared. There's an analogous equation for inductors. After all, inductors are kind of like the electrical equivalent of inertia. The energy associated with an inductor is 1/2 Li squared. So the energy associated with the magnetic field lines of this inductor is equal to 1/2 times, what was the given inductance value? Oh yeah, 1/2 Henry. So 1/2 times 0.5 times current squared. Well, in the steady state, we just found that the current is 30 milliamps, so times 0.03 squared. So what do we get in this case? 0.03 squared divided by 2 times 0.5 gives us an energy of 2.25 times 10 to the negative 4th joules. Okay. Now we suddenly throw the switch back open. Let's think about this. If we throw the switch open, then this all becomes a dead branch once again. And so there's no way current can flow through resistor number 1. But we've already reached a steady state current of 30 milliamps flowing through the inductor. And inductors are devices that, according to Lenz's law, very much oppose a change in flux. And the flux is the self-imposed flux associated with the magnetic field of the solenoid when 30 milliamps flows through it. So as not to lose its own self-imposed flux, it doesn't want to lose the current that's flowing through it that makes that flux. So if it instantaneously wants to maintain that 30 milliamps, then the 30 milliamps has no choice but to flow through resistor number 2. So to find the voltage across points A and B, we just have to use Ohm's law. V equals IR. So 30 milliamps now flows through the 2000 ohm resistor. We can cancel 1000 with milli, and we get 60 volts. Interesting, isn't it? It seems like we're getting something for nothing, in the sense that our battery was 12 volts, and we just found a way to create 60 volts of potential difference. But you'll see that there's no such thing as the law of conservation of voltage. There's just a law of conservation of energy. So it's not a problem to create 60 volts of potential difference in a brief instant in time. That voltage spikes to 60 volts at the moment the switch is thrown open, but this 30 milliamps does eventually die down to 0, and so I believe that 60 volts of potential difference across points A and B just represents a quick spike in voltage that rapidly drops to 0. What's the current through resistor number 2? Well, we just said it. It's 30 milliamps at the moment that the switch is suddenly thrown open. It doesn't stay 30 milliamps for long. In fact, if we were to graph it, the current through resistor number 2 versus time, it starts out at 30 milliamps, but very quickly decays away. Well, when we say very quickly, how quickly? Well, there's a value we can label as tau, the time constant. And the time constant for an inductor in series with a resistor is equal to the inductance divided by the resistance. And at a time equal to that time constant, the current will have dropped from its initial value down to 37% of its initial value. In any case, the current through resistor number 2 at the moment the switch is suddenly opened is 30 milliamps. But if we were to graph the current through resistor number 2 versus time, it would take on this shape. So the final question asks, what's the rate of change of current through the inductor? That's another quantity that decays away. So I think the nature of this question again is saying, at the very instant that the switch is thrown open, what's the rate of change of current in the circuit? Well, let's see. The voltage across resistor number 2 we just found is 60 volts. The voltage across our resistor is 60 volts. But then again, that's no different than the voltage across our inductor. What's the equation for voltage across an inductor? Isn't it negative L di dt? And if we're just concerned with magnitude, then we can disregard the negative sign. So di dt is equal to the magnitude of the voltage divided by the inductance. So it's 60 volts divided by 0.5 Henry, and so we get a value of di dt equal to 120 amps per second. Think about that. 120, a change in current of 120 amps per second, and we were starting with a current of only 30 milliamps. So if you have only 30 milliamps and the current can change at a rate of 120 amps per second, that's 120,000 milliamps per second, then it's practically the blink of an eye or less, right? Less than the snap of a finger. A very short amount of time for the current to drop to zero after the switch has been opened. Maybe we should take this a step further and figure out how much energy would be dissipated through the resistor as a function of time. Yeah, let's do that. We're adding question number 9 to this example problem. What's the amount of energy that gets wasted away as heat in resistor number 2 in that very brief amount of time that the current drops from 30 milliamps and approaches zero? Well, because it's a varying amount of current, I'd like to say that energy is just equal to power times time, but the power isn't going to be constant. Power wasted away as thermal energy in a resistor is I squared times R. But if the current is not steady, then the power is not constant, and so it's better to say energy is equal to the integral of P dt. All right, so let's take this step by step. The energy is then equal to the integral of I squared R dt. Now current is fading away in time. And the equation that describes how that current varies with time goes something like this. The current is equal to the maximum current multiplied by some exponential decay term. It should just be e to the negative t over tau. And tau is equal to L over R. So we can make the substitution that our energy is the integral of I maximum times e to the negative R over LT, that quantity squared multiplied by R dt. And if we're going to find the total amount of energy dissipated in heat, then we need to go until the current really does reach zero. Well, that only happens after an infinite amount of time. So we're going to integrate from t equals 0 to infinity. Okay, so let's pluck the constants out of this integral. We get I maximum times R are both constants, and then times the integral, this I gets squared. Okay, so we've got I squared times R, and then times the integral of e to the negative 2r over L t dt, right? This term is also getting squared. Okay, from 0 to infinity. Well, the integral of e to some constant times t is equal to 1 over c e to the constant times t. Okay, so we get that the energy is I squared r times negative L over 2r e to the negative 2r over L t evaluated from 0 to infinity. Well, this part of the expression is all constant, so we can take it out of here, and we get, oh, wait a minute, I don't like the negative sign. Can I change it to a positive if I change my limits of integration? Yeah, let's do that. So now we get L I squared r over 2r times e to the 0 minus e to the negative infinity. Well, e to the 0 is just 1, and e to the infinity would be itself infinite, or undefined. E to the negative infinity is 0. Oh, so this whole term right here is just equal to 1. Oh, wait a minute. I think we did this the long way. We just found that the energy dissipated as heat in the resistor is equal to, we cancel out those, and we get 1/2 L I squared. Oh, shoot. If we look back here, we realize that was nothing more than the equation we used to find the energy of the inductor before the switch was opened. Oh, of course, by the law of conservation of energy, the energy that was associated with the magnetic field in the inductor, once the switch is open and that magnetic field collapses and sends a current through resistor number 2, all of the energy is dissipated as heat. So if we had 2.25 times 10 to the negative 4th joules of energy stored in the inductor, then after a very long amount of time has passed, when the switch is reopened, we get 2.25 times 10 to the negative 4th joules dissipated as energy through resistor number 2. Actually, I find that pretty satisfying that the equations agree with one another.